Howdy y'all, welcome back to my lecture series on astronomy, ASTR 103, an introductory or survey course in, astronomy. Today we're going to be talking about the Milky Way Galaxy. We're going to be talking about its structure, its formation, and we're going to use that to give us a little bit of insight on the mysterious concept of dark matter. Now, I'll be expanding somewhat on the concept of dark matter in the next lecture when we talk about galaxies in general. But for right now, we are simply talking about our own galaxy and figuring out or talking about how we know what our galaxy actually looks like. I can always mess that up. Dun, 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 dun. Apparently Dr. Rob cannot tech today. There we go. So, Milky Way Galaxy, hopefully, or the Milky Way, I should say. Hopefully you are all familiar with it. Unfortunately, I have to say that because of the advance of civilization, one of the drawbacks of it is a phenomenon known as light pollution. Myself, I wouldn't consider myself too much of a city boy, and I certainly wouldn't consider myself a country boy. I've only seen the Milky Way Galaxy 13 times in my life. As an astronomer, I've been to a number of observatories where the sky is very, very dark. The Milky Way is, you really need a dark sky in order to see the Milky Way, which is kind of hard to do east of the Mississippi. I've been told, out west, Montana, Arizona, you can see the Milky Way quite readily. Now, the Milky Way was called as such basically because of the Greeks. They saw this white, milky sort of band across the sky, and they assumed it was some kind of maybe atmospheric phenomenon that was that was permanent. But in actual fact, what we find is that the hazy band of light is actually dense clouds of interstellar gas and dust that are all shaped within, or all constrained, or primarily constrained, within a disk. Now, just a brief history of the study of the Milky Way. Galileo was the first one to recognize that this Milky Way was in fact not any kind of atmospheric structure, and in fact it wasn't really a cloud at all, but really just lots and lots of stars so tightly packed together on the sky that the individual stars could not be distinguished from one another. And he discovered this by using his telescope. He looked at the sky with the telescope sort of below the Milky Way, and then he scanned through the Milky Way to above it. And what he noticed was, as he moved through the Milky Way, the number of stars in his field of view became much more dense, and then became less dense as he moved outside of the Milky Way. So he recognized that the Milky Way was simply a higher concentration of stars in a band. Later on, the siblings William and Caroline Herschel, who were instrumental in a number of ways in astronomy, primarily in looking at comets and stellar catalogs, they correctly inferred from this that the Milky Way was the Milky Way was disk-shaped, that what they were seeing was in fact our galaxy like a dinner plate if we resided within that dinner plate. And then the first estimate of the size of the galaxy came from a gentleman by the name of Kapteyn. And while he recognized that the Milky Way was a large structure, that the Milky Way Galaxy was far larger than, say, our solar system, it was still far smaller than what we now know. The other consequence of Kapteyn's model, which is basically what's now referred to as the sort of cheese box model, is that he placed us, as we are wont to do, at the center of things. That changed with a gentleman by the name of Harlow Shapley. And what he did was, if you remember back from a previous lecture, I talked about pulsating stars, Cepheids, primarily. And Henrietta Leavitt discovered that the period of these stars is directly tied to their intrinsic luminosity. Long story short, we can use these pulsating variables, these pulsating stars, as a distance indicator. Now, Shapley used a different type of pulsar, or different type of pulsating star known as an RR Lyra, but he looked at these stars in globular clusters that are basically around the sky, and he was able to create a fairly accurate map of the Milky Way. And so he recognized that we were no longer in the center of the Milky Way. We were actually offset about two-thirds of the way out along the disk. He also recognized that the Milky Way was surrounded by a roughly spherical halo of globular clusters. And so this was sort of our first cue, or first clues, as to how the galaxy formed. Now, one of the problems with Shapley's research was that he took from that research that the universe was in fact the Milky Way Galaxy. The entirety of the Milky Way Galaxy was in fact the entirety of the universe. The spiral nebulae that he saw, he believed to be actually within our own galaxy. He was later obviously proven to be proven incorrect, but that is a subject for a different lecture. One of the issues with observing the Milky Way Galaxy is, as you hopefully noticed with the pictures that I showed earlier, with that band across the sky, there were these dark clouds, or dark sections intermixed with them. And those dark sections correspond to essentially interstellar dust. There's a lot of dust and gas within the disk of our galaxy, and what that does is it shields our ability to see beyond that, basically see the other side of our galaxy. We can see towards the galactic center, but really we have a hard time actually observing beyond that. Because again, because of all the intervening stuff, technical term, in the way. Now, we have obviously quite a bit of luminous matter in the Milky Way. Luminous matter obviously is matter that we can see, and we can see this matter on a variety of different wavelengths, all the way from radio all the way up to X-ray gamma rays, and we can map out what the galaxy looks like in each of those wave bands, and depending on what frequency or what wavelength you are observing in, you get indications of the overall structure of the Milky Way Galaxy. For example, if you wanted to study the ISM, if you wanted to study how much hydrogen there was within the Milky Way and where it was concentrated, you would look in the radio part of the spectrum, specifically the 21 centimeter line of hydrogen. But if you were more interested in, say, star-forming regions, where stars are actively forming, then you would look more into either the infrared part of the spectrum, or you would look into the infrared part of the spectrum to find protostars, or in the X-ray part of the spectrum to find supernovas. Because we know that supernovas are essentially tied to very massive stars. Very massive stars are very short-lived, and so that the location of supernovae are fairly well tied to star-forming regions. When we do this analysis, when we look at the Milky Way via these different wave bands, and we look specifically at the stars, what we notice are essentially two distinct populations. Now, these aren't clear-cut. There isn't a hard edge to these. But generally speaking, we have two populations, POP1 and POP2. And for some reason, in my opinion, it should be the other way around. POP2 stars are actually older. POP2 stars came around first. Personally, I think they should be, since they came around first, they should be population 1 stars, but I digress. Population 2 stars are older, they're cooler, they're redder, and they have lower metallicity. What does that actually mean? What that means is, again, if we harken back to our knowledge of stars and how they form, we know that that lower mass stars. Well, let me back up a little bit and basically say that the metallicity, or more specifically, the amount of heavier elements within the universe is increasing with time. Because we know, because of the chemistry, because of the physical nature of how stars evolve, they convert lighter elements into heavier elements. So as the universe ages, the amount of heavier elements like carbon, oxygen, uranium, things of that nature, the amount of those elements increases. So conversely, if you were looking at stars that formed earlier in the universe's lifespan, those would have less heavier elements in them. So these population 2 stars, we believe, were the first stars that formed within the Milky Way, or very close to the first stars that formed within the Milky Way. The reason why they are cooler is because, again, if we look back at star formation, or the history or the lifespans of stars, the hotter, bluer stars, they live fast, die young. They burn out much more quickly than their redder counterparts. And so, given the history of the Milky Way and how old it is, these first O stars, these first B stars, they would have already long died off, because they only lived to be tens or hundreds of millions of years old. Which again leaves the fact that the population 2 stars are redder in nature, because again, these blue stars have long ago lived through their lives and blown up as supernova. But then we notice that there's a subsequent generation. So we have the stars that were formed early. They evolve, they go through their lifespans, the higher mass stars explode into supernova, that material gets redispersed within the galaxy, and then new stars form from that recycled material. And so population 1 stars are younger, they're hotter, they're bluer, and they have a higher metallicity. Or at least the ones that we can see. Really, when I say hotter and bluer, I'm really talking on average. I'm not saying that there are more bluer or hotter stars within the first population. Just on average, if you look at all the stars within the 2 different populations, Pop 1 stars tend to be hotter and bluer than population 2 stars. Which brings us to the overall structure of the Milky Way. Now, if you want to simplify this down to first order, there are 3 structures within the Milky Way galaxy. There is the bulge, which is a central region of the galaxy. There is the galactic disk, where a good number of the stars are located within essentially a very thin plane. And then beyond that, you have a spherical halo of stars, primarily stars within globular clusters. When we look at basically the size extent, the Milky Way galaxy is roughly a circular disk that is roughly 30 kiloparsecs in size, or, let me see, I can do math, about 60,000 light years across. But it's only about 0.6 kiloparsecs in thickness, or about 1.8, there, right, 1.8 light years, give or take, in thickness. So, or 1.8 thousand light years in thickness. Bottom line, really, really thin, really, really wide. The sun, as I said, is not in the center of the galaxy, which is probably a good thing because of the amount of concentration of luminosity that's in the bulge. I'm not sure how that would really work with our habitability, but we are kind of in the boondocks, as it were, in terms of our location. We're about 8,000 parsecs from the center of our galaxy, or our galactic center. Now, when we look at the stellar populations, again, this is a fairly simplistic view of it, but ultimately what we find is that the disk of the galaxy is primarily composed of population 1 stars, and I'll explain why that is in a few slides. So the disk is primarily population 1, the bulge is a mixture of population 1 and 2, and the galactic halo is almost exclusively population 2. And you can kind of see that from this, where you look at the disk, although this isn't a great illustration, but if you look at the disk tends to be a little bit bluer than the bulge. That bulge is more yellowy because there is a larger fraction of older, redder stars in the bulge than there is in the disk. And so when we look at the disk more specifically, what we find is that the galaxy, or the disk itself, contains about 200 to 400 billion stars, or around nearly a trillion, really 100 billion solar masses worth of material, worth of stellar material, and about 10 billion solar masses of dust and gas. So a lot of our mass is trapped up in stars, but we still have a good amount of dust and gas to feed even further star formation. The disk itself is not homogeneous. The disk itself is not basically just one disk like a dinner plate. It actually has structure to it referred to as spiral arms. And these spiral arms are of higher density material and are populated primarily with molecular clouds, and within those molecular clouds that these stars form and sort of congregate. When we look at the orbital motions of stars within the galactic disk, as one might expect, it's very much like the solar system in the sense that all of the stars are fairly ordered. They have a fairly ordered revolution. They have fairly ordered orbits, meaning that they're all pretty much prograde. They all pretty much go counterclockwise around the center of the galaxy, and they tend to keep the same plane. Again, the thickness of the disk is very small. Now, stars have their own peculiar motion. When a star forms, it's going to have a motion which is dictated by its local environment, and it's going to head off in a certain direction. But once it leaves its nest, as it were, and keeps going on the direction, is now sort of dominated by the mass distribution of that galaxy. And again, that mass distribution is primarily locked up into a disk. So if the star is going down below the disk, most of the mass is going to be above it, so gravity is going to pull that star up. And because momentum is the thing, it's going to continue. That star is going to continue to go up, go through the disk, and then once it's on over top of the disk, again, now the mass is below it. Gravity is going to pull it down, and it's going to do this nice kind of up and down motion as it goes around, also circular. This is obviously an exaggeration, but the take-home point is that the stars are fairly ordered. They all kind of go orbit around in the same direction, and all do so in the plane. Unlike the stellar halo, the stars here orbit in, one would say, chaotically, or more, I think the better term would be randomly. It's very much like the corresponding, you can think of the disk as the inner part of the solar system, and then the halo is the Oort cloud. So in the halo of the Milky Way, stars tend to have orbits that can have a wide range of eccentricities. They can have a wide range of inclinations, and so it creates that spherical structure. When we look at the mass distribution, most of the basically there's about the same amount of mass within the halo as there is within the galactic disk, but almost all of that mass is trapped up into stars. The galactic halo has very little gas and dust still remaining within it. And that gas and dust is the gas rather, is at very, very high temperatures. It's very similar to the solar corona because of how rarefied because there's so little gas out there. Any sort of energetic event like a supernova is going to cause that gas to speed up very quickly, and there's little out there to actually cause it to slow down to any extent. So here we're just talking about I'm just talking about the orbits of halo stars. Again, they are primarily random in the sense that they can have any kind of eccentricity, or they're a wide range of eccentricities, a wide range of inclinations. The stars are trapped up in, like as I've said before, the stars are pretty much trapped up in globular clusters. Globular clusters are gravitationally bound groups. They're called globular clusters because they are globular in shape, and they can have memberships of a few thousand or hundreds of thousands of stars, all the way up to some of the bigger ones like the Great Nebula in Hercules that has approximately 1 million members in them. And these, again, are primarily older population 2 stars. And then you get into the bulge. And the bulge is kind of as I sort of think implied before, a mixture of things. It's a mixture of both population 1 and population 2 stars. The orbits tend to be a bit more random. While there is a certain range of inclination, a smaller range of inclinations than you find in the halo, it's a larger range of inclinations than you find in the disk. And so we have one of the problems with studying the galactic center, or the bulge, is because there's a very, very high concentration of dust and gas, which for a long time blocked our view of what was going on inside it. It was only until the advent of, or really the advent or frequent use of infrared observations that we really started to be able to see the interiors of it. In one particular place, the center, as it were, we refer to as Sagittarius A. This slide is basically just talking about what I just rambled on about. The orbits of the bulge, the stars are fairly random. Not as random as they are in the halo, but certainly more random they are in the disk. The Milky Way Galaxy is not alone. As I am fond of saying, stars are social creatures. Most stars are in binary, triples, or quadruples. And then on top of that, you have stars forming in clusters. And then on top of that, the stars also gang together into galaxies. And then the galaxies like to hang out to each other. And so there is galactic clusters. The smallest words escape me today, sort of classification of a galactic cluster is a group, or a local group. A group. And so we refer to the group that we belong to as the local group, which constitutes about 25, 50 galaxies, depending on how you count things, with three major galaxies. We have the Milky Way Galaxy, you have the Andromeda Galaxy as seen from the top, and then you have the Triangulum Galaxy on the bottom right. All three galaxies are spiral galaxies that contain roughly the same amount of 200 to 400 billion stars within them. And then you have a whole lot of satellite galaxies, smaller galaxies, primarily irregular in shape or elliptical in shape, that are just orbiting around each of these big mammoth sort of galaxies. One of the things we're going to be talking about next time is something that I like to call galactic cannibalism. The distances between stars relative to their sizes is very, very large. That ratio of distance to size, of distance to radius, is very, very large for stars. So the chances of two stars actually interacting with each other as they fly through space is very, very small. Not so for galaxies. Galaxies, if you look at the ratio between the distances between galaxies and the relative sizes of radii, that ratio is significantly lower. And so there is a higher chance that these two galaxies are going to interact with each other. When they pass by each other, they're going to interact. And one may, in fact, eat the other one. We see that today with the Magellanic Stream. We can see that at some point, a satellite galaxy got too close to the Milky Way, and it has been ripped apart due to gravitational tidal effects. And we see this Magellanic Stream based on our observations of hydrogen and where the hydrogen within our galaxy and local environment are located. Eventually, fun fact, the bigger galaxies are going to start interacting with each other around 4.5 billion years from now. The Milky Way and the Andromeda Galaxy are going to smash into each other, and a whole lot of fireworks are going to happen after that. The sun probably won't run into anything, but the large molecular clouds are certainly going to smash into each other, creating a whole lot of star formation. So now let's look at the Milky Way in a little more detail in terms of structure, and what does that structure tell us about how the Milky Way formed and how it is currently evolving. So as I mentioned before, we have spiral arms. There is these discrete structures within the disk of the galaxy, which we refer to as spiral arms. They are sort of coherent spiral lanes or lines that run around the bulge, or begin from the bulge and then sort of emanate outward. And we have been able to identify about 4 or 5 different separate coherent structures. The sun resides in what we refer to as the Orion Cygnus arm. Then you have the Perseus arm, and so forth. How do we know that there are spiral arms? Because we've mapped out stars. We know the distances to stars, at least on our side of the bulge, where they're much easier to observe. And we notice is that there are gaps in the distances. We know that there are a lot of stars which correspond to sort of a distance corresponding to the Perseus arm. Then you have stars that are about the same distance away from the galactic center as the sun, and then you have stars, say, that are in the Carina Sagittarius arm, are all roughly around there. So when you look at the distances of stars away from the galactic center, they tend to cluster up, and those clusters, the best explanation for those clusters is they reside in these arms. Another way that we see these spiral arms, another evidence that we see in these spiral arms is, again, looking at the hydrogen. If we can trace where the hydrogen is using radio astronomy or radio observations, we can, again, find out that the hydrogen seems to also collect itself within these discrete regions or discrete lines or discrete distances around from the galactic center. We also see that with molecular clouds. We also see that molecular hydrogen also tends to group within these spiral arms, and incidentally, because of the fact that these molecular clouds are in these spiral arms, that's where we see star formation. O and B type stars, these bright, massive, hot stars, these are also located in those regions as well. Now, why this galaxy, or why does the Milky Way have spirals or spiral arms? Because there are lots and lots of different galaxies that don't. There are elliptical galaxies, there are regular galaxies, they don't have spiral arms. So why is it that the Milky Way does? Well, the long answer is far beyond the scope of this introductory course, but the short answer is that we have what is known as a density wave. When the Milky Way collapsed into a disk, there were these compression waves that were set up as as the galaxy spun up due to conservation of angular momentum, and these compression waves were very roughly created due to the fact that the galaxy is not homogeneous. There are areas that were more dense than others, And so over time, these instabilities or these differences in density set up these density waves. These so small disturbances became amplified over time, sort of a runaway effect. And so you have this material of stars, dust, and gas that were constrained to this disk, and because of this spiral wave, or these compression waves, which this spiral structure came into existence. So here's a kind of an overall picture of it, where you have that. So you think of the spiral arms as kind of a slinky, laid out on a table. And you can if you oscillate one end of the slinky, you're going to have basically a longitudinal wave. You're going to notice within your slinky that at times the rings in the slinky are closely packed together, and at times the rings of the slinky are far away from each other. So on the right of this diagram, where you basically see a few stars, but really nothing there, that would correspond to the part of the slinky where the rings are away from each other. Now the ring, or the arm, where you have a lot of material, these blue and colored blue and yellow pockets and so forth, that's where the rings of the spiral arms are. The rings of the slinky are compressed, and it's that compression that really aids in star formation. Because again, if we harken back to our discussion of star formation, I talked about molecular clouds, these giant complexes of molecular hydrogen. And stars form when there are density irregularities within that cloud that allow for gravity to collapse smaller regions of that cloud into smaller and smaller components that make up stars. Unless there is some way to really get that, to really squash that down, that molecular cloud down, gravity isn't the fastest thing in the universe, particularly if the mass is very widely distributed. So it helps star formation if that gas can be compressed via some different method, in this case, that compression wave. And so as the material kind of gets squished into these arms, those molecular clouds also get compressed, which activates star formation. And then you see these O and B type stars that form, and then these hot regions, which we refer to as H2 clouds, which are basically cavities within those molecular clouds that are being illuminated or excited by the amount of energy coming off those O and B type stars. Now, the galactic center is very much higher density than the bulge as a whole. Essentially, you can think of very much like globular clusters, or really any kind of spherical distribution of matter. You're going to have a denser core than you are sort of the outer envelope of it. And and because of that, you have, you can think of it, because again, density is related to star formation. The more dense you have, the denser region that you have, the more active star formation that's going to happen, and the younger the star is going to be. And so it turns out that the galactic center has a much higher density of population 1 stars, hot blue stars, than it does population 2 stars. I've lost my train of thought. So again, just to kind of restate that, because of the enhanced amount of gravitation that occurs within the galactic center, that is essentially what triggers that starburst, that enhanced star formation, which occurred fairly recently, within the last 200 million years. And that is why we have such a high population of inner stars. Which also probably explains why our galaxy is not an active galaxy. I'll explain what active galaxies are in the next lecture when we talk about galaxies in general. But what I mean by not an active galaxy is that there is not a lot of dust in the very, very center of our galaxy. Because within the center of our galaxy is a giant monster, as it were. It's a supermassive black hole. We knew prior to this, due to radio signals, that there was some sort of structure within the center of the black hole that was emitting radio waves, or was creating radio waves in some sort. And so Dr. Andrea Ghez looked at this region to try to find out what may in fact be there in the infrared. And she and her team made very detailed, very precise measurements of stars within that area, such precise measurements that she could actually see the stars move over that 20-year time frame. Now let's see here. Can I get this to go? There we go. So you can see in the upper right is a time-lapse, a looped time-lapse of 20 years worth of observations of these stars. And they are, particularly if you look at the smaller one, that is a star that is moving on the order of the solar system, a little bit beyond the solar system, on an order of 20 years. That may seem like a long time, but astronomically, that is just basically a split second. What I'm trying to emphasize is these stars are moving at very, very high rates of speed, and they appear to be orbiting a center. As you can see from the bottom diagram, you have these, we can basically plot out, we have enough data there that we can plot out the orbits of these stars, and they all seem to be orbiting a big fat nothing. Which is odd, because usually, in order to orbit something, there has to be mass there, and if you have mass, then that mass is usually lit up. So the fact that it's orbiting a big fat nothing is the precise evidence that we have that there must be a supermassive black hole there. And what I mean by supermassive is there is a black hole in the center of a galaxy that is on the order of around 4 billion times the mass of our own sun. 4 million times the mass of our own sun. What's a few orders of magnitude, my friends? So this black hole, 4 million suns, would be the equivalent of 4 million suns in mass. Which brings us to rotation curves. Now, we will come back to this subject again when we talk about galaxies in general, but what we find, or when we look at the motions of stars in the disk itself, not in just the bulge, but in the disk itself, we find something rather peculiar. Based on Newtonian physics, these stars are not moving, or classical mechanics, these stars are not moving relativistically, and they're not localized in a really deep gravitational field. So classical mechanics still is very useful and can be applied in this situation. Well, Newtonian or classical mechanics tells us that if you were to look at the velocities of these stars as they orbit around the sun, or excuse me, as they orbit around the galactic center, the velocity should drop as you move outward. This is basic Kepler's third law, a consequence of Kepler's third law, which basically relates the orbital size of a planet to its period, is that the velocities of planets that are further out are slower or smaller than velocities of planets that are further in. The velocity of Mercury going around the sun is larger than the velocity of, say, Jupiter going around the sun. We expected the same thing to happen here. We had a large central concentration of mass in the center of the galaxy, and then the mass peters off as you move out in the distance. So we expected the velocities to peak within the bulge and then peter off as you go outward. But we didn't find that. What we find is that it peaks, as we would expect, within the bulge, And then the velocities stay basically constant as you move further out into the galactic center. We made these observations primarily through, again, looking in the radio, when we look at the velocities of basically gas clouds in stars within the galaxy using, the Doppler effect. But we notice that these velocities do not decline as we expect. They actually basically hold steady. And this is not the Milky Way is not peculiar in this. Further studies of other galaxies also reveal that further studies of spiral galaxies also reveal this sort of behavior. What that means, what that physically means, is that in order for that to occur, there has to be more mass on the outer edges of our galaxy. The mass is not centrally located within the galaxy. The mass is evenly located. So instead of a solar system analogy, we actually have a merry-go-round analogy, where the mass is fairly evenly distributed throughout the galaxy. But that's not what our observations of luminous matter tell us. When we look at the amount of luminous stuff, technical term, amount of luminous stuff out there, we expect, or we see, that there is less material in the farther regions of the galaxy than there is in the inner parts of the galaxy. So what's going on there? What could possibly explain this? Which leads us to something we refer to as dark matter. Just as an aside, dark matter and dark energy are not related. They have the same name, but really the term dark simply means unknown in this case, or not explained in a way. Also, with dark matter, it's also an even easier kind of explanation. This is matter which is dark. We can't see it, or at least we do not know the technique at this point to detect it. And based on modeling of these galaxies, of our Milky Way galaxy and other spiral galaxies, what we've determined is that in order for those rotation curves to exist, then the amount of matter, the fraction of matter, 90% of it has to be dark, only 10% of it is luminous. Now, where exactly is this dark matter, and what exactly is it? Still active fields of research. What we can say is that dark matter is fairly evenly distributed, again, throughout the galaxy, hence the rotation curves. And so we imagine dark matter existing in this halo. Now, people have asked me about, how does dark matter affect the sun, or how does dark matter affect us? The simple answer is that it doesn't. Dark matter is huge in extent, but on smaller scales, it's essentially insignificant. While it contains a huge amount of mass, that mass is contained within a huge volume. So while it has implications to galactic structure, it has almost no effect on small-scale structure like stars, planets, and so forth. So we know that this dark matter halo, I should say that we can infer that this dark matter halo exists based on the evidence that we have, and also because of these observations that we've made, primarily again of hydrogen gas, we know that dark matter halo, or highly suspect, that dark matter halo is far larger than the stellar halo. So, okay. So what is dark matter? What is dark matter? What can explain this matter that we cannot see? And so there are essentially two categories of candidates. One of them is, at this point, is sort of becoming the favorite among the two. But the two categories are massive and dim and weakly interacting. Now, what are massive dim objects? Basically, they're normal objects. They're regular sort of objects. They're planets. They're black holes. They're small galaxies, potentially. These are objects that are, their luminosities are low, meaning that it's basically an observational effect. The mass is there, and the mass is luminous, but it's so dim that we just can't see it. The argument is if we had better telescopes, if we could actually see fainter objects, then we would discover all of these massive objects, all these very low mass stars, white dwarfs, potentially evidence of small black holes, neutron stars, things of that nature. So that's the idea behind massive but dim, is normal matter that just doesn't put out a lot of light. The reason why massive and dim is not seen as the most likely explanation for dark matter is that there has been analysis of how much material, how much hydrogen and how much helium would actually be produced within the Big Bang. And from that analysis, it's been concluded that the universe simply did not create enough of this material to actually explain this. There's just not enough material for these dim objects to actually exist. So which brings us to the other sort of, again, the leading candidate. I won't say the most probable candidate, but it is a leading candidate as a leading explanation that we have, is weakly interactive massive particles. And in this, when I use the term massive here, what I really mean is that a particle has mass. Best example of this that I can give you is a neutrino. A neutrino is a particle which is generated through nuclear fusion within the sun, and it's weakly interacting, meaning that it streams at relativistic speeds, very close to the speed of light, and it streams through anything without interacting with it at all. Pretty much, it can interact, because we have detected neutrinos, but the vast majority of the stuff just streams through material, streams through normal matter, without bothering to basically interact with it in any way. There's no exchange of energy, there's no exchange of mass, or anything of that nature. But we know, but they have very, very little mass. We have, the experiments that we've run tell us that while these neutrinos must have mass, we do not have the technology in order to detect such a small mass. And so this is the idea, is that this dark matter is composed of these weakly interactive massive particles. There are other explanations that say that the matter is exotic. It is not what we refer to as baryonic, protons, electrons, the normal matter that we see. So really what I'm getting at is, while we have leading explanations, while we have sort of the explanations that we find to be more probable, this is still very, very much of an open question. And we have set up experiments such as the Large Underground Xenon Detector, as seen here, to help look for dark matter, particularly these weakly interactive massive particles. And so far we haven't found any. So far we have not been able to detect matter which would sufficiently explain what we see observationally in these large galaxies. Which brings us to the formation of the Milky Way. And this is really where dark matter kind of comes into play. So when the universe was created, you had a tremendous amount of material being formed through nucleosynthesis, still not pronouncing that right. The very early universe was very, very hot, basically just a giant energy field, and then that turned into a giant field of plasma, and then eventually that cooled off. And then you have these, and along with that, when it cools off, normal matter, or luminous matter I should say, coalesced, and dark matter coalesced. And again, as with a lot of things that I've talked about, this is not a homogeneous process. There are denser regions in the universe than in other regions. Apparently, there are a lot of herons out today. And it is these denser regions of dark matter that gravitationally brought luminous matter together and allowed gravitation to basically be able to squash or collapse these gas clouds quick enough that they formed within the lifetime of the universe. Without dark matter, without the existence of dark matter, the idea that galaxies could exist within the lifespan of our universe becomes more unlikely. Formation of the Milky Way happens very similar to that of the formation of a star. You have a very large prenatal galactic cloud. As that cloud collapses, the small amount of rotation that it has increases due to the angular momentum. The inner part of the cloud, which would, and by analogy, turn into the protostar, turns into the galactic bulge, and then the rest of the material falls into a disk. And so our clues for why we believe this explanation to be the most probable is that the halo would have collapsed first. And again, this giant cloud is also not homogeneous, so you'd have smaller pockets of denser areas. These would form the first stars. These stars would hang out in clusters, and so the halo has a much higher population of population 2 stars. Again, the first stars that formed. These are older, redder, have lower metallicity, and then as the cloud collapsed down, we have higher concentrations of more active. Let me back that up. Let me rephrase all that. So you have this cloud of gas as it's contracting. Again, not homogeneous, so there are denser parts of that gas, or denser parts of that cloud. And from those, you have these globular clusters form. During that case, in the sort of the outer regions of this cloud, particularly in the outer regions of the cloud, that formation, that collection, or that creation of stars, severely or significantly decreases the amount of ISM material or interstellar material, a lot of the dust and gas, the components, the building blocks of stars. Those stars basically used up a large portion of it during their creation, which is why today we don't see a whole lot of dust and gas in a spherical distribution around the galaxy. That also explains why we don't see active star formation within the halo of the galaxy, because there's just not any more gas or dust to form stars there. And then, as the gas collapsed down into a disk, it became even denser, and that's why we have active star formation within the spiral arms. And so, essentially, this slide basically just reiterates what I was talking about. You need you need dark matter to be the primary reason why luminous matter comes into. You need dark matter to be the primary reason why luminous matter collects and gets squashed into stars and galaxies. Without that, the collapse of the luminous matter we believe that the collapse of this material, the formation of luminous matter into stars and galaxies, would exceed 13 billion years, which is what we currently estimate the age of our galaxy, primarily due to observations of stars within the galactic halo. Again, just reiterating what I was talking about in terms of as the cloud collapses, you have the formation of globular clusters first, and then it forms into a rapidly rotating disk. And with that, I am going to end basically just with this slide. It's Again, just reiterating that as the galactic disk formed, you had enhanced star formation due to these spiral density waves. You have a supermassive black hole formed within the bulge, the galactic bulge. Now, really quickly, I do want to take a step back. One of the more fascinating questions, one of the things I love, one of the, I can't seem to speak today. Thank you for having patience with me. There are certain facets of astronomy I find most fascinating, or more fascinating. Exoplanets being one of them. Young stars are star formation being another. The other is active galactic nuclei, these supermassive black holes. Now, it's still very much of an open question as to how these supermassive black holes formed. Did they form first, and then the galaxy formed around them? Or did the galaxy form and just have a central concentration of stars that were formed, and then these stars essentially just merged into each other? You know, went supernova, and then all these black holes just basically just formed into, just fell into each other, creating a supermassive black hole. That's still not quite solved yet. We don't have a lot of confidence telling us whether or not one of these hypotheses is more likely than the other. And then finally, when we talk about the evolution of the Milky Way Galaxy, the Milky Way Galaxy is ultimately going to fall prey to galactic cannibalism. Given us long enough time frame, all of the galaxies within the local group are going to form into a much larger galaxy that is elliptical in shape. And again, we will talk more about that in the next lecture. So, with that, I will stop my blethering on. I hope you have found this enjoyable, or I hope you have found this at least informative, if not enjoyable. Please, I hope you enjoy the rest of your day, night, morning, whatever happens, and peace out, and I will see you next time.